Hello all. In the last class, we tried to understand the process of vector quantization and which was extended to your learning vector quantization process weight operation. So once again, let us try to recall that learning vector quantization is a kind of supervised learning. It is a combination of two steps. One is the self-organizing map. Second one is the vector quantization process. It can be better understood using the picture given below, given in front of you. That is picture number 2, just in the bottom of the screen. This one. In this picture, you may see that there is input vector from the n-dimensional input space, which is mapped to a finite space using self-organizing map. And further, this finite space generated by the self-organizing map is further to be grouped in the form of clusters or in the form of classes by using vector quantization process. So these two terms, means self-organizing map and vector quantization, gives a direction leading to the linear vector quantization based neural network and performs the supervised classification in particular. The overall architecture or the overall connections of LVQ are almost the same as that of your Cohen's self-organizing map. Let us try to understand that this is your presynaptic layer, neuron number 1, neuron number 2, neuron number n from the presynaptic layer. This is your postsynaptic layer containing 3 neurons, this one, and this is your weight vector W1, this is weight vector W2, and this is weight vector W1. So the architecture remains the same as that of your Cohen's self-organizing map. Now let us again try to recall the similarity calculation formula, which is the Euclidean distance given by your ED for neuron K, and if the updated part, or you can say the extension of self-organizing map in terms of LVQ, is only that if the winning neuron comes out to be the K, or you can say this is the O of K, means the observed output, observed winner neuron is your K, and if the observed neuron belongs to the same class as shown by your target in the input data, then we have to strengthen the weights by using this formula, this one. If your observed class, observed winner, is not same as that of your input pattern, then the overall weight is to be negated and is to be updated using this formula. So this is the weight updation mechanism to be used by the learning vector quantization process. These two steps means finding Euclidean distance, then declaring the winner, and then comparing the winner class with that of the already given class of the input pattern, and then accordingly making adjustments to the weight is repeated till the convergence is not reached. Let us go through a numerical example. So the problem here is to cluster the input space containing 6 patterns given by this feature matrix I, representing 6 patterns I1, I2, I3, I4, I5, and I6. So this is your feature matrix representing 6 patterns, and your vector T, that is your target vector, gives the class of each of your input pattern. Means I1 pattern belongs to class 1, I2 pattern belongs to your class number 2, I3 belongs to class number 2, I4 belongs to class 1, and so on. And this is your random weights, or you can say weights being initialized. So just by looking at this problem, we can imagine the structure of our LVQ. LVQ will be having 2 layers, presynaptic layer and postsynaptic layer. Your presynaptic layer will contain 4 neurons. Your postsynaptic layer will contain 2 neurons. Each of the postsynaptic layer neuron will be connected to the 4 neurons of your presynaptic layer, and hence the W1 will be having 4 weights. In the same way, W2 will also be having 4 weights. So these are your weights for W of 1. These are your weights for W of 2. These are your 2 weight vectors. And for simplicity and to be more particular, that the output grid to be formed is of 2 dimensions, which is the case for most of the Cohen self-organizing maps. Learning rate is fixed to be equal to 0.9. 0.9 is your learning rate, and this learning rate decreases by half after each epoch. So let us start understanding how the LVQ will be classifying this given input space. The first step is to pick the first pattern from a list of 6 patterns, means first pattern of your first epoch. Find the Euclidean distance for cluster number 1 for pattern number 1, for cluster number 2 for pattern number 2. Euclidean distance will be equal to weight minus the input feature. So 1 minus 1, this one for the weight, this one for first feature value, this one again the weight, this one second feature of first pattern, third feature of first pattern, and the fourth feature of first pattern. This comes out to be 0. In the same way, the Euclidean distance for the second cluster comes out to be 16. So just by looking at the distances produced by, or you can say through Euclidean distance, we see that cluster number 1 is the clear winner, being producer of minimum Euclidean distance. So we have to update, and before updation, we have to check the condition whether the winning class, or you can say winning cluster generated by your self-organizing map is same as that of your given input pattern target or not. If it is same, then we have to strengthen, otherwise we have to weaken the weights. So in this, in the case of this first pattern, which was belonging to your class number 1, this one, first pattern was belonging to your class number 1, and the Euclidean distance for this pattern number 1 is also first. So the first cluster is the winner for first pattern. It means the cluster number shown by the LVQ and that was given in the input pattern space are equal. So we have to strengthen the weights. We have to upgrade the weights in a positive way using this formula, and using this we updated the 4 weights, and accordingly we modified this for the weight vector corresponding to the first cluster. Now we updated the weights. Now pick the second pattern and apply the LVQ on this pattern using the modified weights. So we picked the pattern number 2, epoch number 1, and found the Euclidean distance using this formula. Again, for cluster number 1, it comes out to be 16. Cluster number 2, it comes out to be 0. Now again check whether the winning neuron number is same as that of the desired output class or not. So in case of second pattern, the output class expected was equal to 2, and the class generated by the LVQ is also equal to 2, because this distance is equal to 0. So it is the minimum one, and so will be declared as winner. So target is equal to that of the observed class from the LVQ, and hence the weights are to be strengthened using the same formula, this one. So we updated the weights, and the new changed vector is this. So again we obtained the modified weight matrix. Now pick up the third pattern. We picked the third pattern of the given input space, and then again applied the Euclidean distance formulation, and found the Euclidean distance for cluster number 1. It comes out to be 8. Cluster number 2, again, it comes out to be 8. So both distances are equal. It means we have to consider both as the winners. So both are winners and we need to update their weights according to the condition whether the actual output, actual target class is same as that of the winner cluster or not. So the third pattern of your input was belonging to class number 2. It means we'll be updating the weights for cluster number 2 in a positive way using this formula, and weights of cluster number 1 in a negative way using this formula. So we updated the weights in positive direction for cluster number 2 and in a negative direction for cluster number 1. And this is going to be our new weight matrix. So that this weight matrix will go to the go for the next pattern, that is pattern number 4. Pattern number 4 is applied with the help of those changed weight, and again the Euclidean distance was found, which comes out to be equal to 0.25.68 for cluster number 1 and 10.48 for cluster number 2. Clearly cluster number 2 is the winner, but the target for the fourth pattern was the class number 1, and what is the winner for class number for pattern number 4? It is 2. So again there is a mismatch. It means we have to weaken the weight matrix, weight vector for cluster number 2. So we weaken the weight vector and a new vector comes out to be equal to this one. Now it comes now go to the fifth pattern, apply the fifth pattern using the changed weight. Again find the Euclidean distance, then 14.48 and 41.83. This one is the winner being the minimum one, so we need to update its weight. Now look at the actual class of pattern number 5. It is equal to 1 and the observed, or you can say produced by the LVQ is also 1. So we have to strengthen its weight. Its weights are strengthened using this formula, which are coming out to be these, and your latest weight matrix will be this. So with take this weight matrix to your pattern number 6 and again find the Euclidean distance, which comes out to be 8.06 for cluster number 1, 20.95 for cluster number 2. So the clear winner is your cluster number 2, but the actual class of the pattern number 6 is 1. So again there is a mismatch. So we'll be weakening its weights using this formula, and after weakening the new weights are coming out to be this, and this will be your new weight matrix. Now it completes your first epoch, and we have to run many number of epochs of this kind. Suppose, or you can say consider that at the second epoch the learning rate will geometrically decrease 0.5 times. Therefore the learning rate will be 0.45 for the second epoch, and after running 1000 such epochs the learning rate will comes out to be equal to this one, and the final weight matrix after 1000 epoch will be this one. And if we apply the 6 patterns using these weights, then the output cluster generated by our LVQ will be like this. It means the pattern number 1, the pattern number 4 and pattern number 5 will be clustered, will be classified to your cluster number 1, while pattern number 2, pattern number 3 and pattern number 6 will be classified to cluster number 2, which was the actual requirement, which was our target before we started learning using the LVQ. Means these condition, these input and pattern, input and output mapping is just satisfied by your LVQ algorithm, LVQ learning process. So it will complete the LVQ learning process, and now our LVQ network is ready to use for any new coming pattern to be clustered or to be classified in the existing class. Let us also go through the other application. In this, what we want to have is that there are 10 digits, 9 digits ranging from 1 to 9, which are written by different person, different learners in different styles also. So we collected 25 such patterns which were written in a grid of 9 is to 7. Means 9 number of rows and 7 number of columns were there. Each writer was asked to write 1 in this grid, 2 in this grid, 3 in this grid, and up to 9 in this grid. And in such a way, total 25 patterns were collected from different writers. This is the actual count of different characters. Means digit number 1 was represented using pattern number 1, 2, and 3. For example, one of the writer wrote 1 in this way. Means if we join the ones, it will come out to be the shape of 1. And again, if we join the 1 in this way, then this again will come out to be 1. This is again represented by some other writer. Means he wrote 1 like this. So in same way, the 8 was written by some writer. Just keep on joining the number of 8s, number of 1, sorry. So this is the representation given by some writer, and so on. Means there were 20 such patterns collected from different writers representing different number of digits ranging from 1 to 9. This is the actual picture. Means 2 was represented using 3 patterns, 3 was represented using these 3 patterns, 4 was represented using this pattern. So the actual task was to classify these 20 patterns in 9 classes. Means what we actually wanted is that whatever the pattern is coming, means in whatever way the 1 is written, whether it is 1A, whether it is 1B, whether it is 1C, the system, the network should able to classify it as 1. This is the main purpose of the LVQ network for this problem. So it started making the LVQ network, and actually the LVQ network, which is a combination of 2 layers, pre-synaptic and post-synaptic. So in this case, your pre-synaptic layer was containing 9 multiplied by 7 number of neurons. Means 63 number of neurons were there in the pre-synaptic layer, and the post-synaptic layer was containing 9 classes, 9 clusters. And we followed the process as traced in the previous example. And after a number of iterations, or you can say after 1000 number of epochs, these are the results. Means class 1 was containing pattern number 1, 2, and 3. Just try to match it from here. Class number 1 was representing 1, 2, 3. So it correctly classified all the patterns to digit number 1. Class 2 was containing pattern number 6. Class 2 again was containing pattern number 6. 4 and 5 are missing from this class. In the same way, just try to observe class number 3, 4, 5, 6, and up to 9. You will find that it successfully classified most of the patterns in its correct class. However, some inaccuracy was there, but that can be improved by just setting some hyperparameters, or some increasing the number of epochs, increasing or decreasing your learning rate, etc. You can apply many combinations of them. So there are chances that this accuracy get improved. So there are so many other applications of learning vector quantization also. You may just explore by yourself. And also we will be discussing some more in near future. So it completes our learning vector quantization. process.